Hello and welcome to my channel once again. In today's lesson, we are going to continue with trigonometry, and specifically we are going to look at trigonometry ratios. In our previous video, we looked at what a right angle triangle was, because we said that in trigonometry we study the angles and sizes of right-angled triangles. And we said that a right-angled triangle is a triangle with one of its angles being 90 degrees. So in today's lesson, we are going to consider the right-angled triangle below labeled ABC, where one of the angles at A is 90 degrees. The slanted side BC becomes the hypotenuse. Now there are two angles left aside the 90 degrees angle, and these are the angle at B here and the angle at C here. So with respect to the angle, whether at B or at C, AC and AB have specific names, just like the BC. So let's consider an angle represented as theta at B. Then the side facing the angle, which is this side, becomes our opposite. Then the side on which the angle theta lies is now called the adjacent. So with respect to the sizes and the location of the angle, each of the three ratios in trigonometry can be found. Let's look at the sine. For the sine of theta, it is the opposite over the hypotenuse, where the opposite is B and the hypotenuse is A. So in this case, sine of theta will be equal to B over A. Then cos of theta will be equal to adjacent over hypotenuse, which is equal to C over A, and that of tan of theta will be equal to opposite over adjacent, which is equal to B over C. The three trigonometry ratios here can be summarized when we look at the first letters within the ratios. For example, for sine, the first letter is S. For opposite, the first letter O. Hypotenuse here, the first letter H. This can give us what we call the SO. Then for the first letter in cos, which is C, first letter in adjacent, which is A, and first letter in hypotenuse, which is H, can give us the K. Then for the first letter in tan, which is T, first letter in opposite, which is O, and first letter in adjacent, which is A, will give us tua. When we combine the three, we have SO, Ka, tua, which we can easily use to remember the three trigonometry ratios. Now let's also consider the triangle here, where we already said that BC becomes our hypotenuse. The slanted edge is always known as the hypotenuse. If the angle is now located at C, AB here is no more the adjacent, but the what? Opposite, since it is the side facing the angle at C, or the angle theta. Then the angle theta now lies on side AC, which will now become our adjacent. So in this case, the three ratios changes. The sine of theta will now be equal to C over A. That of cos of theta will now be equal to B over A. And tan of theta will now be equal to C over B. Let's take note here. We said sine of theta should be C over A, cos of theta will be B over A, and that of tan of theta will be C over A. When we are to find the ratio of C over A and B over A, that is, if we are dividing them, the division sign eventually changes to multiplication sign. And the second fraction, which is B over A, changes to A over B, because we change the division sign to multiplication. When we do that, this gives us C over B, because we have like terms here, A here, we'll cancel A here, leaving C over B. When you look through, you realize that C over B is equal to tan of theta, whilst C over A is equal to sine of theta, and B over A is equal to cos of theta. So in this case, we can see that tan of theta, that is C over B here, is as a result of dividing sine of theta by cos of theta. So simply put, we can say that tan theta is equal to sine theta over cos theta. Also, since we have a right angle triangle, we can apply Pythagoras theorem. And from the Pythagoras theorem, the hypotenuse squared, which is A, should be equal to B squared plus C squared. Let's divide through by A squared. When we divide through by A squared, this gives us B over A all squared plus C over A all squared equal to 1, because A squared cancels A squared. But we know that B over A from here is equal to cos of theta. C over A from over there is equal to sine of theta. So in place of C over A, we'll put sine theta. In place of b over a, we'll put cos theta. So substituting, this gives us cos theta squared plus sine theta squared equal 1. Expanding them, we'll have cos squared theta plus sine squared theta to be equal to 1. Or we can say sine squared theta plus cos squared theta is equal to 1. So this is one of the trig identities. Sine squared theta plus cos squared theta should be equal to 1. Also, we can say tan of theta is equal to sine of theta all over cos of theta. Let's look at solvable examples where we can apply trigonometry ratios. For example 1, if you are asked to find the value of theta in this particular diagram, we'll see that in order to find the value of theta, with respect to the position of the angle theta, the opposite will be known, which is 7 centimeters, and the adjacent is 12 centimeters. So from the 3 trigonometry ratios, the ratio which involves opposite and adjacent is tan. So we are going to say that tan of theta will now be equal to opposite over adjacent, where we know opposite is 7 centimeters and adjacent is 12 centimeters. So tan of theta will now be equal to 7 over 12 since they are of the same units. Then finding tan inverse of both sides, theta will now be tan inverse of 7 over 12. Correct to the 2 decimal places. Theta will be equal to 30.26 degrees. For example 2, in order to find the value of theta, with respect to the position of the angle, the 24 centimeters here becomes our adjacent, whilst the 25 centimeters here becomes our hypotenuse. So in this case, our adjacent is 24 centimeters and the hypotenuse is 25 centimeters. So the ratio involving adjacent and hypotenuse is cos. For that matter, cos of theta will be equal to adjacent over hypotenuse, which will be equal to 24 over 25. Again, they are of the same units. So theta will be equal to cos inverse of 24 over 25 when we take tan cos inverse of both sides. So that gives us theta to be equal to 16.26 degrees to 2 decimal places. For example 3, we are asked to find the value of x in this particular diagram. To find the value of x in this particular diagram, with respect to the angle 50 degrees here, 12 centimeters becomes the opposite, then x here becomes our hypotenuse. and the only ratio involving opposite and hypotenuse is sine. So sine of theta is equal to opposite over hypotenuse, which implies sine of 50 degrees should be equal to 12 over x. Cross multiplying, that gives us x sine of 50 degrees to be equal to 12. Dividing through by sine of 50 degrees for x to stand alone, that gives us x to be equal to sine 12 divided by sine 50, which gives us 15.67 centimeters. The three trigonometry ratios can either be positive or negative depending on the quadrant in which it is found. Let's consider the quadrants here, where in certain cases we call them the Cartesian plane. With the Cartesian plane, we know that this is our x-axis, positive, x-axis, negative, y-axis, positive, y-axis, negative, and this is our origin, which bears a numerical value of 0. So in trigonometry, the x-axis is associated to the cos, then the y-axis is associated to the sine. Then since in trigonometry we start from the first quadrant, or we read angles in anti-clockwise direction, we are going to start from the positive x-axis. That is our reference. So from the positive x-axis, this becomes our first quadrant, where the angles between the first quadrant lies within 0 and 90 degrees. So for the first quadrant, we can find all the three trigonometry ratios. We can find sine in that particular quadrant, cos in that quadrant, and tan in that quadrant. But you can see that in the first quadrant here, since we have here y-axis, which is positive, and remember we said y-axis is for sine, so the sine should also be positive. Then the x-axis here is also positive, so the cos should also be positive. Since we have x positive and y positive, anything found within the first quadrant should be positive, so tan should also be positive. So in the first quadrant, all the three ratios are positives. That is why we have this here representing all the three ratios. Then in the second quadrant, where angles lie between 90 degrees and 180 degrees, the sine is positive, since we have positive y-axis. But since we have negative x-axis, that means the cos will be negative. And the tan should also be negative. This is because in each of the quadrants, aside the first quadrant, only one of the ratios should be positive. So in the second quadrant, it is only sine that is going to be positive. So we use S in the second quadrant to represent our positive ratio, that is the sine. Now to the third quadrant, where angles are between 180 degrees and 270 degrees. The sine will be negative since the y-axis here is negative. Then the cos will also be negative since the x-axis here is also negative. But that of tan should be positive because we said one of the ratios should be positive. So representing the positive ratio, that is tan by t in the second quadrant. And let's look at the final and the fourth quadrant. Angles within this quadrant lies between 270 degrees and 360 degrees. In this particular quadrant, since y-axis here is negative y-axis, the sign should be negative. But when we come here, the x-axis is positive. That makes cos to be positive. Then tan will also be negative since one ratio should be positive. So representing the positive ratio, which is cos by c. When you look at the letters represented by each of the quadrants, starting from the fourth quadrant in anti-clockwise direction, it spells cast. So in order to easily remember this as to which ratio should be positive or negative in which of the quadrants, we use this system, and this system is called the cast system. Let's now look at how we can apply the signs with respect to the quadrants to the ratios. For example, if you are given cos of x to be 8/17, where x is acute, and they ask you to find tan of x over cos of x sine x, or sine of x plus tan of x over tan x minus sine x. Let's look at how we can solve these examples. Let's take for the example 1, representing the given ratio, which is the cos of x here. The cos of x is 8/17. 8/17 here, and they said x is acute. That means x is less than 90 degrees but greater than 0 degrees. That is, it should lie in the first quadrant. So this is our first quadrant. So we are going to indicate our x degrees here. So this gives us our x degrees. This is the x. Then if this is x, we know cos is equal to adjacent over hypotenuse, k. So our hypotenuse here is 17. Our adjacent is 8. That leaves this side, which is the opposite, which we don't know. So we represent it by ven. We can easily calculate for ven. Since we have this as a vertical line and a horizontal line, they meet at 90 degrees. So this gives us a right angled triangle. We can apply Pythagoras theorem, where from Pythagoras theorem, v squared plus 8 squared should be equal to 17 squared, the hypotenuse squared. So v squared plus 64 should be 289. Grouping your like terms, v squared should be equal to 289 minus 64, which is equal to v giving us square root of 255, and square root of 255 is 15. So that means v here is equal to 15. So since we have v, we can find the two remaining ratios, which implies that tan sine of x will be equal to our opposite, which is 15, over the hypotenuse, which is 17. Then tan of x will be opposite over adjacent, where our opposite is 15 and adjacent is 8. Since we now know that cos of x is 8 over 17, sine of x is 15 over 17, and that of tan of x is 15 over 8, it implies that tan of x over sine of x, cos of x sine x, will be equal to 15 over 8 over 8 over 17 multiplied by 15 over 17. And simplifying this, we'll have 15 over 8 divided by this division sign. This here is changed to the division sign here. Then 8 by 15 gives us 120. 17 by 17 gives us 289. Simplifying this, we'll have 15 multiplied, or 15 over 8 multiplied by 289 over 120. If we change this division sign to multiplication, we change the positions of the numerator and the denominator. So simplifying, we'll have 289 divided by 84. Because 15 will go into itself, 1. Then into 120 gives us 8. 8 by 8 gives us 64. The 1 here by 289 gives us 289. In order to find the solution of the second example, which is sine of x plus tan x all over tan x minus sine x, this will be equal to 15 over 17 plus 15 over 8 all over 15 over 8 minus 15 over 17. This then gives us 120 plus 255 divided by 136. That is when we find LCM here. LCM will be 136. 136 divided by 17 gives us 8. 8 by 15 gives us 120. Plus 136 divided by 8 gives us 17 by 15 gives us 255. All over 15 over 8 minus 15 over 17. The LCM again will be 136 divided by 8 gives us 17 by 15, 255 minus 136 divided by 17, 8, 8 by 15, 120. So this will also be 255 minus 120 all over 136. When we simplify, we'll now have 375 over 136 divided by 135 divided by over 136. That is, when we add this, we have 375 over 136. Then this division sign, the over here is changed to this. Then we'll have 255 minus 120, which gives us 135 all over 136. Let's change the division sign to multiplication. This will now give us 375 over 136 by 136 over 135. 136 will cancel 136 here, they are common, leaving 375 over 135, and we can cancel. When we simplify, 375 135 will be equal to 25 over 9 to the simplest form. That is, when we divide 375 by 15, we get 25. 135 by 15, we get 9.